All right, so we're going to do a quick example here. And this is an example of how we could use the knee voltage diode model to look at a circuit here and see what the currents are going to be. So we've got this voltage source that's 12 volts. We have this resistor that's 200 ohms. And we have these three diodes that are hooked up in this configuration. So we've got one diode right here, and then we have in parallel with that single diode, we have these two diodes that are in series. So whatever current is flowing through this diode is going to be the current flowing through that diode. So that's what this ID2 equals ID3 is saying over here. Okay, so we're assuming that these are silicon diodes, and we're curious what the current is going to be through each of these diodes. So I'm going to have you guys sit and think about that for a minute, and your hint is going to be think about which branch, so either this branch or this branch, which one is going to start conducting first and what its voltage will be. And then I also want you to remember that things that are in parallel have to share the same voltage. So I'm going to give you guys a couple minutes and try to think through and see if you have a guess as to what the currents are going to be in this case. So I'm just going to be quiet for a minute here. I'm going to let you pause the video, and then I will work through this. Okay, I'm going to assume that you actually paused it, even though I'm guessing that a lot of you probably didn't. But we'll go through it. So I'm going to get out of annotation mode so I can scroll down. And here is our solution. Okay. Okay. So simple answer is one of the branches is not going to have any current flow through it at all. So only the first diode is going to have any current flow. This is our circuit up here. We have Vs equal to 12 volts, our little resistor, our diode, and then our other two diodes. All right. So in order for this diode D1 to conduct, it's a silicon diode. So, whoops, sorry about that. We have a silicon diode, and it has a forward voltage of 0.7 volts. So that means we have to have at least 0.7 volts applied in order for this to have current flow through it. And once current does start to flow through it, it's going to be fixed at 0.7 volts. Okay, so what does that mean for us? Well, this is fixed at 0.7 volts, and we need to see if these two are going to be able to conduct. So this also needs 0.7 volts in order to have current flow through it. This needs 0.7 volts to have current flow through it, which means across this whole branch here, we need to have these added up, which is 1.4 volts. That's what we need across both of these in order to have those two have current flow through them. But we're never going to get that high because this now has current flowing through it. It's fixed at 0.7 volts. We're never going to get up to 0.4 volts because these are in parallel. These have to have the same voltage. So we're not going to have any current that can flow through that second branch. It's all going to flow just through this part of the circuit. Okay, so that's just our little bit of conceptual analysis that we need to do to simplify the circuit. Then once we have this, this looks a lot more familiar, and we know how to solve this using the knee voltage diode model. We just use this formula right here, where we take our source voltage, subtract the knee voltage, divide by the value of R1, and that's going to give us our value of 56.5 milliamps. And then based on our earlier simplification, we can also report the current for the other two diodes, and that's just going to be 0 amps because they're never going to have enough voltage to actually have current flow through them.